There's a few more free response questions. There's 2015 free response questions having to do with some molecular forces. The first one they want you to do is draw this over here. By the way, when you see the two dots there, that's just a bond. So you have bond, bond, double bond, bond, bond. Those are just bonds in there. You can draw bonds rather than individual dots. Actually, we had this one, another one. Where carbons almost always form 4 bonds. If you add up your total number of electrons, there's 20 new lone pairs on oxygen. I'm not going to go through that. What's the approximate value of the carbon oxygen hydrogen bond angle in the ethanol molecule? This is the ethanol one, is telling you that. So what's the angle of this? Well, it'd be very similar to water. Remember, if you have 4 bonds, tetrahedral shape, the bond angle is 109.5 degrees. Well, in this case, 2 of those bonds are off. You have an oxygen in the middle. 2 of those bonds are off, and you have lone pairs. Remember, that decreases that bond angle by a couple of degrees typically per lone pair. Say something a little bit less than 109.5, and it should be fine. All right. There was more to this question, but it says, during a certain dehydration experiment, C2H4 and unreacted C2H5OH passed through a tube into some water. So they had these two things were being produced, going through a tube into some water, bubbling into some water. They're both gases bubbling into some water. The C2H4 was collected quantitatively as a gas. In other words, they measured exactly how much they got, but the unreacted C2H5OH was not. Explain this observation in terms of the intermolecular forces between water and each of the two gases. So you need to tell what forces are between this and a water molecule. So if you had another water molecule close to it, so you would say this is nonpolar, only has dispersion forces. There would be dispersion forces between these two things. You could say there's dipole-induced dipole forces, but you could just say there's dispersion forces between those. Whereas between this and a water molecule, you would have dispersion forces, dipole forces, and hydrogen bonding between these two things. So this has pretty strong attractions to water. It's probably fairly soluble in water, so it'd be hard to collect it quantitatively. You wouldn't be able to tell how much is in there because it would bubble into the water and dissolve in it. This would bubble through the water. You could collect it. All right, 2017. This is chromatography, which I'm not sure if I've shown this in class yet at this point in time, but what they do is you put some dyes on a piece of paper, like maybe a marker, maybe a red one, green one, blue one, something like that. You put some liquid in there, and the liquid will move up the paper. The liquid will, by capillary action, will move up the paper. Okay, so notice they have a non-polar solvent right here. So this is the beginning. There's an unknown dye right there on this one in the same non-polar solvent. And here's where they end up at the end. So this is where dyes A, B, and C ended up. Notice C traveled the farthest and B the least. So that tells me, and also if you read down here, it will say that, I think it tells you that the chromatography paper is polar. So remember, like kind of dissolves like likes, other things are like it. So since C went the farthest, it was attracted to this solvent moving up the paper. So C is probably the most non-polar. B is probably the most polar. It was attracted to the polar paper, did not get attracted to the liquid moving up the paper in there. They probably ask what the unknown is. It's not a great question. The unknown, I think, is probably closer to A than B. The fact that it went past B, I'd probably say the unknown is probably dye A. It's probably the one it's closest to from there. That's all we got.